Let's talk a little bit more about uniform circular motion. So what we've learned so far is that if we had a circular path, and this is our path, that if we know the speed, in this case we can draw the velocity, and the velocity is tangent to the path always. If we know that magnitude of the velocity or the speed, and we know the radius, then we can calculate the centripetal acceleration as v squared over r. And we get the direction as always pointing inwards. It points in towards the center of the circle. So to form a vector, you get your location on the circle and then find the perpendicular to that. You know how to do that. You've learned how to find the slope on a graph and make a line to that point using point slope formula. And then you also learned how to make a perpendicular line to this. This is I think pre-cal stuff. That perpendicular line would be the line that is in direction with our acceleration. So it always points inwards or towards the center. And that's exactly what centripetal means, is center-seeking acceleration. Now, Newton's law, second law, says that if this is indeed some acceleration, that a force had to cause it. And we learned if the acceleration is equal to v squared over r, then we can substitute into Newton's second law for the acceleration. So let's just plug in the centripetal acceleration and we get mass times v squared over the radius of curvature. I want to make a note real quick. Sometimes you'll see this as v squared over rho, or I might say that. In that case, rho indicates the radius of curvature, and this could be for any path function. So if you had y as a function of x, and it looked like this, and I wanted to find the radius of curvature at this point, what is this radius? If it's y as a function of x, well, we have a formula for that, and where did I write it? We get rho as 1 plus the first derivative with respect to x squared, and then this whole thing is raised to 3/2 power, and then we divide that by the absolute value of the second derivative. So to find what the radius of curvature is, if you know some crazy path function, it's not circular just like this one. This one and the ones we're studying right now are uniform circular motion. It's a perfect circle. If you had the formula or the equation of your path, you could take the derivative, so you'd need the first derivative and the second derivative, and just plug them in there. And then you would evaluate this whole thing at some x is equal to value. Everything would be in terms of x, right? So you could just actually get a number. That number would be in meters, or whatever units your position versus position graph is in. Okay, let's also take a look at a couple examples. One, let's talk about, and these are in your book, a car going around a corner. And we'll say it has a constant speed for the time being. It could be speeding up while it's going around it, in which case not only would it have an acceleration vector pointed inwards, it would have one tangent to the path. So its total acceleration in this case would look something like that. For right now, let's just use a constant velocity, constant speed. Alright, now what we need to think about is when you're going around this, let's say you're in a vehicle going around a corner. The thing making you go around this corner is the friction between your tires. And actually, in this case, we'll do a banked turn problem in a little bit where this is at some angle theta, and we bank it for a reason. But let's think of a turn that is where our car is not going to be banked. It's going to actually stay perfectly level. The road is at an angle equal to 0 degrees from the x-axis. Alright, so here's my sweet car. It is going around the corner like this. Maybe a top-down view would be better. Okay, so the whole reason the car is making this corner at all and actually taking a curved path is because you're giving the vehicle steering input. And as a result of that, it is causing a reaction. The friction between the tires and the road is causing a reaction force that is acting in the direction of your curvature. So if we're curving to the right in this case, our acceleration would be to the right. Well, some forces have to be causing that. Now think when you're sitting inside the car though. Oh, let's use a different color. When you're sitting inside the vehicle, maybe here's the seat, here's the person, steering wheel, their head, and these are the tires. So the force while they turn the wheel to the right is putting a frictional force causing the vehicle to go in the direction of the acceleration, which is towards the center of the circle. But what's happening to you? You've got a seat here, and you've got your butt here. Well, to a certain point, to some certain radius of curvature, or some certain speed, depends on both of those, right? V squared over R. Your butt's providing enough friction with the seat of the vehicle to keep you in the center of the vehicle, or in your same spot at least, right? At some point, maybe you start turning even more to the right or taking a sharper turn. The radius is then decreasing, or maybe you're speeding up. Then maybe your body actually goes to the right and the side of the door is actually holding you up. The car is still exerting a force on your body, whether it be on your butt or whether it be from the car door or whether it's from you holding onto the steering wheel or your feet on the floor. All of those are keeping you in place, and it's gonna cause you to have the same acceleration as the vehicle. Now let's look at a different case. If we looked at Earth and maybe some sort of satellite going around it. Oh, that's not a circle. That looks pretty decent. Oh, a little off. So here we have Earth, and there could be some satellite going around it, and any satellite, any two bodies traveling around each other, or you look at one body traveling around the other, even though they're actually traveling around each other. The shape is always elliptical, and that's one of Kepler's laws. In a little more advanced mechanics, we'll do some more of Kepler's laws. He has 3, but one of them says that when something orbits another object, the center of one of them is at the foci. So in this case, we would have a foci at the center of Earth. And the second law says that the same law says that they travel in ellipses. An ellipse is something with the formula x squared over a squared plus y squared over b squared is equal to 1. But for right now, let's talk about just circular paths. So let's make a circle, and this is going to represent some sort of satellite or something that we're in. Give it a different color. And in the satellite, there's also going to be us. So it could be some sort of space station, some distance r from the center of Earth, not from the surface. And inside this space station is us, or a person. Now, there's a difference between the car problem that we just talked about, where the car and the person take the same path, versus this type of problem. This is called a central force problem. In this problem, there's only one force ever acting on us and acting on the capsule that we're in, and it's always pointed towards the center of our ellipse in this case. It always points that direction, and it keeps us on track. And since the object or the satellite or whatever we're in has the same force and acceleration, right? We have the same exact force and acceleration acting on us. It ends up being independent of mass. And since we have the same force and acceleration as the capsule, we travel along in the same path. So as the space shuttle moves along in a perfect circular path in this case, we move along in a perfect circular path also. We don't move inside it. In the car case, the wall ended up keeping us in place, or the friction in our butt. Otherwise, we would keep going in a straight line, right? Always think about what happens if you're standing there swinging a string over your head with some mass on it, and you let go of this thing right when it's at the top. It always takes a path directly tangent to wherever it was snipped off at. So wherever the perpendicular is to the string, its path after it's snipped is directly tangent to its circular path at that point. That's very similar to what's going on here. If you're in your vehicle and you didn't have your vehicle, or the friction between you and your vehicle holding you in the same direction that the car is traveling in, your body would just want to go straight. So that force you feel on your body when you turn isn't there because there's some central force acting on you. It's there because frictional forces are acting on you, because frictional forces are acting on the tire. In this type of problem, a central force problem, the only thing acting on us and the space shuttle thingy is gravity. the force due to gravity. And since the magnitude is equal, we end up traveling in the same path. One more note on, I don't think I went over it yet. Yeah, our centripetal force we just calculate with b squared over r now. I think that's it. I'll do a couple examples. One will be just a car moving in a flat turn. It's sample problem 6.05. I'll make a video about. And then we'll see what happens if we make the turn banked like I talked about. What if we wanted to know what angle theta would allow us to drive with a velocity of 100 meters per second around a curve with a radius equal to 200 meters without having any friction between our tires at all, or in other words, without having to touch the steering wheel. The car would take the turn on its own. And this is what banked turns pretty much do for you on the highway. Don't take my word for it or go out and do this, but like if there's some sections on 215 where the highway turns, it is absolutely banked a little bit. And that serves a couple purposes. I'm not a civil engineer, but I know that it does serve the purpose of water drainage. You don't want water on the road. You want, I think, at least 2 axes of water drainage at any given time. And but number 2, it is going to help keep you in your lane and take some wear and tear off your vehicle. The frictional force and the tires and the road are both going to wear down less. So your tires will last longer, the road will last longer, it's safer. There's multiple reasons why we engineer things like that. And we use physics to do it. There you go.